Okay, so good morning, everyone. Welcome to this third year of CLAPEM. Before we start with the plenary talk, I would like to make several announcements. So first of all, is to remind you that we are editing a special volume of this conference. So you're all welcome to contribute to this volume. This will be edited in the Birkhauser series that is around. Actually, Birkhauser House is here promoting some of the products they are editing, and we will have this special volume. Also, there is a change tomorrow for the course of Vincent Tension. So he will not be lecturing in this room. He will be lecturing in the auditorium that is just next to this building across the road. So when you go out of this building, go to the right, cross the street, and then go to the right, there is the entrance to this auditorium, to that auditorium. Also, it's important to say that today there is no registration, but you have to run if you want to go to the conference dinner. We still have some places left, and it's a very good opportunity to taste very original food from Mérida. It's actually one of the best restaurants in Mérida, and also the place is really nice. It's a very nice old hacienda where they used to produce Heineken in the old times. Also tomorrow we have an assembly about CLAPEM in the evening, and I think that's it for the announcements, for the advertising. Some years ago, and he has been actually traveling all around. He has been contributing with a lot of people in many universities. I remember the first time I met Pablo, and actually I met several times Pablo in France. He was working with people in the laboratory of Paris 6, but also I have found Pablo in other places. And he's well known for promoting probability in the region. In his times in Brazil, he's one of the persons that started this famous school in probability in Brazil, the summer school in probability. Well, it's actually winter school in probability, isn't it? And he has also organized many of the previous CLAPEMs. He also trained a lot of researchers, young researchers, and he has been quite active. So today, Pablo will be speaking about Poisson processes of objects and box ball systems. Thank you, Pablo. Welcome.
Okay, it's a great honor for me to give a plenary talk or semi-plenary talk in this meeting, because this meeting has a long story. Started when the Uruguayans that escaped from the dictatorship. The CLAPEM started when the Uruguayans escaping from the dictatorship in Uruguay went to Venezuela, and the LARC was the branch of the Bernoulli Society for Latin American that afterwards, some 20 years ago, became also CLAPEM. It's a good opportunity for me to remember the repression against the people, students, professors, and workers in Chile and Bolivia. And I think we should, maybe CLAPEM should make, and Ecuador also, and CLAPEM should make a declaration about these facts. Okay. Today I'm going to give a kind of mixed talk because we'll have two parts. One is a Poisson process of objects, that is a very old subject in probability, but it's a little observation that we obtained when working in random interlacements applied to as a representation of part of the representation of the the spatial random permutation leading to the Bose gas. But this was too short to give a 1 hour talk, so I decided to give part of some work that I was doing on the ball box system. So this ant is really ant. There is no much connection between the two things, besides the fact that they are nice, I think, and somehow understandable. The first one, I hope, will be understandable for a big fraction of the audience. The second one has nice pictures, so if you don't understand exactly the mathematics, maybe you can guess it. And so I hope that you will enjoy these things. Okay, so Poisson process is, everybody knows what it is. You need an intensity that is a function. I will make a Poisson process in RD. So you have an intensity that is a function from RD to R plus that is locally integrable. And then you have a countable partition of RD. You can think in boxes, okay? And then for each box A, and you want these are bounded sets. So when you integrate the function over one of these sets is finite intensity. And then for each one of these sets, you associate a Poisson random variable and a sequence of random variables with density given by this intensity function normalized to A, okay? So, and then you define the Poisson process as the union over the sets on the partition of these points that are independent and distributed according to the intensity function in the box. If the intensity function is constant, then you just take uniform random variables in each one of the boxes. And so this is a constructive way of defining the Poisson process. Then it's more or less easy to show that if you take another partition, you get the same property, so that the number of points in each box of the other partition will be Poisson, and given that you have n points in the box, then each one of them will have this distribution. Okay? Okay, now I want to construct, so this is the property that I just said, and then now I want to construct a Poisson process of lines. So the Poisson process of lines has some literature, but it's not that popular. Now there are some work by Wilfried Kendall that somehow he claims that the routes in England are distributed as a Poisson process of lines. So suppose that you have L is the set of infinite undirected straight lines in RD, in R2, let's say. This will work in RD. So imagine that you have R2 here, and then you have these lines that are crossing this place, exactly. And then you want a Poisson process of lines. So you want that if you take a set of lines, and you have a disjoint set of lines, you want to have independence as in the point Poisson process, and distributed as a Poisson random variable. For instance, the simplest sets, disjoint sets, are the sets that you take the lines crossing a bounded set A of RD, or R2, and you want that this is Poisson. In this case, I will take a lambda equal constant, so the intensity will be lambda times the volume of the sets. Of course, they are not disjoint. You have to take, if you take another set, you ask the lines that cross the other set but do not cross this one. And this is a way to construct a locally finite set of lines. So the intensity in this case will be sigma finite. this is essentially is to define. I want to define something that has this property. So the classical approach is to map the set of lines to the band 0p times r. I will show a transparency now. And then consider a homogeneous Poisson process on this band with intensity measure lambda. So what you can do is say, well, if I have a line here, this line you can identify by two coordinates. One coordinate is the distance of the line to the origin, and the other coordinate is the angle between the x coordinate and this and the line joining, realizing that distance. Okay, so from this line you have this point here. Here is 0p because you consider only angles from 0 to p, because if not you repeat the lines. Okay, and then and this distance corresponds to this thing. So this line is mapped to this one and vice versa. Okay, this is a bijection. Okay, the line you define this way, and then you get you can get a Poisson process in this region that you can construct as we constructed in the first transparency, and then from this one you map to the circle here. Here the circle are all the lines that the distance is smaller than this radius. Okay, and the angle could be any one. Okay, so the circle exactly is mapped to this region of the space of points. Okay, so since you have this function L that maps points to lines, you can construct your intensity measure as mu lambda of G. G is a test function as the inverse of L computed on G. Okay. Okay, the Poisson line process has the intensity for the circle. Here is a computation, but it's not the conceptual, this computation. You just compute, and you see that the area in the band of the circle corresponds to 0p to p times 2r. So it's the perimeter of the circle. Okay, now if you want to compute the number of lines crossing the convex set, I took this picture from some transparencies from Lentejuol, or Lentejuol. I don't know if someone knows him. You want to compute the mean number of lines crossing a convex set, and then you see, I am sorry, but this picture is cut now. The more important picture in the talk is cut. Ah, no, here it is. Can you help me here put in no continuous? Okay, so you see, if you fix an angle alpha, you fix an angle alpha, the number of, the intensity of the lines crossing alpha will be this W of alpha. That is, you project the convex set in the direction perpendicular to alpha and compute the length of this length, okay? And then if you rotate overall alpha, you get this formula. This formula. So this formula comes from the direct observation of the intensity of the lines crossing the convex set. So this distance are all the lines, is the intensity of all the lines crossing at angle alpha, perpendicular to alpha, okay? This identity here, I don't know a simple way to show it. This, you have to go back to Santa Lo. Okay? If someone has a trivial or intuitive proof of that, I will like to see it. But this is not important. The important thing is this formula. So this is the number of lines that, the intensity of the lines crossing a convex set. Okay, now once that you know that, that a line crosses a convex set, then the distribution of the lines will be this one. So it will be the density of the distribution of the line will be this W, that is the angle divided by the perimeter. And then if you have another convex set, D prime, inside D, and you know that the line convex cross D, then the probability that it also crosses D prime will be the quotient between the two perimeters. Okay, now my goal here is to show that, to show another way to construct it that I guess is in some sense more intuitive, and also you don't need to have a mapping to a point process in order to construct it. So this construction goes like that. You take A equal to R2. LA are the set of lines that intersect A. And then now X is in R2, okay, or RD. So this is the line that passes through X and has angle theta. So it's different. So theta is different than alpha. It's perpendicular, in fact, to alpha. Okay, and now you pick an X, pick an theta, and take a line L, and then you compute the length of the. You don't need to be convex here. You compute the length of the line inside. Inside A. This is A, sorry. It was convex before, but that's not needed. And then you devise, so you take a Lebesgue measure in X times 0p, and then divide by the bias by 1 is over this length, okay? And okay, this will be the intensity, and now you define mu of G as in the case of the Poisson process that I was taking the sum over all the convex. You take a partition of the R2 with bounded elements, and then you take mu of G, you take this measure computed in set AN, but then you ask that you take only the lines that do not cross the sets that you have visited before. Okay, so this gives so the lines that you take the lines that cross AN that do not cross A1, AN minus 1. Okay, and then you the bias as before, and this will be the intensity measured at infinite volume. Okay. So this will be the unique infinite volume measure satisfying that for any set A, you have that, if you restrict the lines that, that cross A, you will get the QA that I defined before, that is this one. Okay? So in this way, you have that each line is represented by 1 point, and this 1 point is the one that you choose initially. Okay, so I take, I call S prime the Poisson process on L with this intensity mu, and then I have a theorem that says that that the Poisson process S1 S prime has the same distribution as the Poisson process that we obtained by mapping the lines into that set of points. Okay, so the only thing that we need to show is that if you take a convex set D, for instance a box, then you will get the intensity of lines that cross D. In fact, yeah. So we have to show that. This is something that I discussed recently with Julio Rossi, how to prove it, because we have the theorem but not the proof. So, but finally Julio helped us to have also the proof that, as you can see, it's not very hard. It's just Fubini and integrate. So you have your, you want the lines that cross D. So you take integral over D in X, integral 0p d theta, and then you divide 1 over Lx theta inter D, and then you just change the interchange integrals. And then this part here, this integral here, you are integrating X over this volume. And for each X, theta is fixed now. For each X, you are taking 1 over this distance. Okay, and then you can express this if you take, so you are, this is the same as to take this double integral here. You take U in this region, in 0 W, and V in 0 L UA. So LUA is this line that crosses here, passes through U here. And then you see that this thing just simplifies to 1, and this thing is W of A, so you get the same density. Okay, so this is the main point here. Okay, now if you want to construct the Poisson line process in the space, you just take a partition of A1, A2, etc., and then you generate the lines intersecting some set A. For each S in this Poisson process and A, you accept the line S theta, because you have this Poisson process here, no, in RD times 0p. So a point of this Poisson process has a point in S and an angle theta. And then you accept the line with probability 1 over the length of the intersection. And then you do that for each set, but then you start with empty set, and then and no lines, and then you apply this construction to AN, but then accept the lines of AN, the accepted lines, so the accepted lines of AN that do not intersect the previous sets, and this will be a sample of the uniform Poisson process of lines in RD. Okay. That's it for this part. For the Poisson, no? Okay, now I will do something very similar to random interlacement, because I don't know if you are familiar with them, but now instead of lines, we want random walks with some transition probability function P of xy continuous in R2 or RD, doesn't matter much. So the space will be the space of infinite, double infinite trajectories. So this is the function from Z to RD. And then I define a random variable that is the projection Wn of W will be the position of the endpoint, and this has an origin. And then I have this probability that is is the distribution of a doubly infinite random walk with, well, independent, identically distributed increment random walk is the same, starting at x0 of w equal to x. Okay, then Snitman, who introduced the random interlacements for the Brownian motions, and then Lawler and Trujillo Ferreras did it for random walks in ZD. They proposed an approach, because now we need to define the lines, these random walks that cross a finite region in RD. So, because these lines are coming from infinity, pass by, and then it's not, you have to do something because you don't know how to do it. You cannot map this line to a point, and, as we did for the straight lines. So they define what is called the entrance time. So you have a trajectory, and this trajectory is coming from infinity, and there is a first point that enters in A, and this first point has some coordinate, and this coordinate I call TA of W. W is the trajectory, A is the set, and TA of W is the coordinate of the first point of the trajectory into the set. And then Snitman proposed to define the capacity. So this intensity function that is, I call Q capacity of A applied to the test function, is just the expectation function of G multiplied by the indicator function that the first time that the trajectory visits the origin is at time 0. Okay? In other words, you can take, so the intensity of a point will be, to have a trajectory, will be, to be this first point will be this so-called equilibrium measure. That will be the probability that the probability that starting from that x, all the past is outside the box. So is the probability that the random walk starting from x, that is inside A, in time -1 is out of the box, time -2 is out of the box, is always out of the box. And the capacity is called the integral of this thing, okay? And then he says, okay, I construct a Poisson process in A with this capacity, and then you can do something similar as I did for the straight lines for the other boxes, or also you can define an infinite volume. You can define an infinite volume intensity. Okay, so working in that Bose thing, we discovered that, and this is some work with Inés Armendáriz that is here, and Sergio Yuchman. We discovered this other way to do it. I don't claim that this is totally original, but I haven't seen it in the literature. Okay, so you consider the number of visits of A. So this is the number of times. So this is time for the random walk. The number of visits is the number of times that the random walk the random walk W visit A. Okay, so, and then you define Q A uniform. You define Lebesgue measure for the point in the box, and then you divide us by the number of visits. And this, okay, and this is a second. It's not totally obvious that this is the same as Q cap, but we'll see in the next transparency that it is. So let me introduce the time shift of a trajectory. When it's just look from time 1. So you shift by 1, you look at time 1, shift by I, you look at the trajectory from time I. And then also you have this reversibility of the Lebesgue measure for the random walk. So this is the same as what I am saying here, that you have a trajectory and start your initial point starts from some x in the Lebesgue measure. This is the same as a start at time 1 from the Lebesgue measure. So, and then construct the thing. Okay, and this. Okay, so this we take now a function g that is invariant by under translation. For instance, the number of points in the box, or the number of points that are at distance less than 1, or things like that. But you don't want to have a space in this g, only the relative relation between the points of the trajectory. And then for functions like that, you have that the two intensities are the same. And the proof is easy also. So you take GA if G is, this is 1. So you know that X is inside A. So TA is less or equal than 0. Okay, so, and TA so could be any point less or equal than 0. So this thing is 1. Okay? And then you take out that, and then just change the integral with summation. And then here, by reversibility, I can just take a translation by I. Okay, so I make a translation by I because of the formula I had in the previous thing. And then when you translate the trajectory, now your 0 will be minus I, but I change it here, the sign. So, and your I will be 0. And the G over N will be theta I of G over N, okay? But now, now you have the theta I of G over N is G over N, because N A is shift invariant, and G was shift invariant, so I can just take out this thing, and then put the sum again inside, and then I get this sum that cancels with the N of A. So you get the identity, okay? Okay, then you show that any of these measures satisfies compatibility. So if you have a bigger box and compute the measure, and then you project over the smallest box, you get the previous measure, and also additivity, that if you have disjoint sets, you can sum the intensities. And then you introduce an equivalence of trajectories by shift. Two trajectories are equivalent if they differ by a shift, and take the space with quotient with this equivalence relation. And then you have a theorem that is also proved by Snitman at that time, that you have an infinite volume measure that I call Q random interlacement. That is the projection of this K over the class of equivalence. Okay. And then you get random walk interlacements. Once that you have this intensity, you have this process that I call gamma random interlacement rho. It's a Poisson process on W tilde with this intensity. This is exactly the same as in SNIT. So one way then to construct the random interlacement, you take a Poisson process S of points, the points of constant intensity rho, and a bounded box S, lambda, and then to each box in lambda, you sample a double infinite Gaussian or random walk, and accept the walk with probability 1 over the number of digits. And then the accepted walk will be a sample of the random interlacement intersecting lambda. Then in RD, you get a partition as before, and then you do it for each lambda, but reject walks starting at lambda j that have points in previous boxes. And then in this way, you construct random interlacement in the whole space. Okay, so this is the part of the first line of my title, and here starts the second line. So this will be an abrupt change. This essentially is this second part of the talk has also two parts, but I don't think I will talk about two of them because I have 20 minutes, right? Or 25. Okay, so I will talk about just a small part, just a part of this work. This box-ball system was introduced by Takahashi Satsuma in '96, and then at some point Zook came to Buenos Aires and gave a colloquium in differential equations, in the colloquium, but he was in differential equation, and he presented this box-ball system that I will not describe here. And it has a property that it's a transport equation, so you are transporting balls in boxes to the right in some way that I don't want to lose time here. And you can identify, and then Takahashi Satsuma identified the solitons. So given a configuration, you can identify parts, you can partition the boxes into solitons or records. Records, okay, so you need to have less balls than empty places. So you have to have density less than 1/2. So the records will correspond to those places that always to the left you have more spaces than balls. And the rest things will be excursion between two records. So you have a random walk that is going down, and then sometimes it goes up, and these mountains are excursions, and then the other things are records. Okay. Okay. So I will take this soft excursion because I allow to come back to 0, so you can think that this is 0, and this will be going down. And this is coming from infinity, but I will take only this excursion. And I will describe how you partition in solitons. Here is this. So what you do is take the, you can just guess how you do to color, how do you color it's not trivial, in fact. So okay, so you start up. So the runs will be what you have zeros and then ones, zeros and ones, zeros, or ones and zeros, ones and zeros. Each of these segments are a run. Then if you have a single, so you can think that you have an infinite run coming to the excursion, then the excursion, and then an infinite run of zeros, no? An infinite run of zeros, or minus ones if you want. From zeros, then the excursion, and then infinite run. So if there is only an infinite run, there are no solitons. If not, you look for the leftmost among the smallest runs. So you look for the small run, the first small run. So it will be size 1 in our picture. And if the run contains 1, then you pair the boxes, the boxes of ones with the first boxes to the right. And if the run contains 0, you pair it with the boxes to the left. That will be 1. So if the run contains k elements, then you will map k zeros with k ones, or you will map k ones with k zeros. But always you will have, sorry, the other way around. Always you will have k ones followed by k zeros. Okay? And then let's do it, the simulation here. So our smallest run here is this one, no? Oops. The smallest run is, so you can, let's suppose that you don't know anything about the colors. You look for runs. The smallest run is this one. Okay, it's a 0, because 1 is up and 0 is down. It's a 0, so you identify this and this as a soliton, and you put a color. Okay. And the next smaller run is this one. It's a 1. You map with the following one. You have this one. Okay. Now you imagine that this, and I call a 1 soliton, this thing. This is a 1 soliton, and this is a 1 soliton. Now you collapse the boxes occupied by already identified solitons, and then, so you have to assume that here these 2 boxes do not exist, and these 2 boxes do not exist. So this, you have a run of 5 here, or 4. You have a blue run of 4 here, and then black, or there, no? You have a run that's going down. Now the next smallest run is size 2. If this one is 0, so you map to the left, you get this one, and then this one also you map to the left. The next smallest run will be this one. This is 3, and you map is a 0, so you map with this one, and then you will stay only with the blue things here. So you will have this run will be 4, and you map, no, this run, sorry, this run will be 4, you map with this other thing because all the other colors do not exist. And then this run you will map with this one, okay? So then you have the soliton decomposition of your excursion. Okay, now, now you can see that you can put 1 solitons. So I can think that this 1 soliton is inserted into this thing that it will call a 1 slot. So this part of the configuration I paint violet. That means that in this box I can put 1 slot. Okay. 1 soliton. So this will be called 1 slot. So all these places that are painted here violet are places where I can put on the right 1 slot. And then all the places that are painted red here are the places where I can insert after it 2 slots, 2 soliton. And the green things are the places where I can insert a 3 soliton. So, for instance, here you say, well, but this, what means that you can insert a 3 soliton? This 3 soliton is inserted in this 3 slot because this 3 soliton belongs to the boxes between this 3 slot and this 3 slot. Okay. Okay. So this you need more than the time that I have in this talk to grasp that. But you can believe, maybe in the following assertion, that you can, given a configuration, you can identify the number of K solitons appended to each K slot. Okay? And the point that I'm going maybe to wake you up, we have shown with David that if the excursion is coming from a random walk, then the number of K slots that the K solitons that you can put in each K slot is geometric and independent of the number of solitons that you put in the other slots. In each K slot, the number of K solitons, in this case, this is 1. You can, in this picture, there are only 1, but you can put, for instance, the blue. You have 2 blue solitons appended to this. Blue solitons are 4 solitons appended to this 4 slot. Okay. now you have this classical tree representation of excursions. That for those that know, this talk is, in fact, is done for those that already know this. Okay, so from this you can identify the tree and then give a color to the branches of the tree. So if you have a tree, now I will color the branches in the following way. At the first step, I give a different color to all branches. I put same color here, but it should be different, because I know how it will finish. But you put a different color to all branches, and then you go to all leaves, and then you go down one step, and you give the color of the rightmost branch, the rightmost son or daughter of this of each node. So here you give the same color, same color, but here you give the right color blue, and then this keeps the original color, that is violet. And then you go one step down, and then you take the rightmost color here and here, and then you go a step down, and you get this coloring. This coloring, if you put it back to the tree, is the same as the coloring I gave for the excursion. But this has a nice, you put back the color. So there is a relationship between branches in the tree and the solitons in the excursion. And here, those squares that were in my soliton things are these arrows, colored arrows here. You have the record is represented, the record of the excursion is represented by a black dot, and then you have only one slot. This slot is to put a branch of 4 slots. So this is a slot 0, and then then you put 2 branches. You put the 2 branches, and then in the branches you can put green. So three branches to these places, but not to the right, because of our construction. And then you have these 3 slots for 3 branches, and then you put your 3 branches here, and then you have all the 2 slots. And then you put the 2 branches, and you have the 1 slot, and then you reconstruct your soliton decomposition of and then you put back this to the excursion, and then you get the same soliton decomposition, so the same K slots. Okay, so the message here is this one, that if the excursion comes from a random walk with probability lambda and 1 minus lambda, but lambda less than 1, than half, then the number of K branches in each K slot is geometric with parameter Qk of lambda. That is an explicit expression of lambda. This is a result with David Gabriele, and it's in archive. There are 2 papers, so it's the second one. And it will appear now. I submitted to some proceedings of the school in Mexico last year. So these are proceedings there. Okay. I have no more time to talk about the box-ball system, but then I will show you a simulation. Who help? You can help me here. Escape. Me pones la simulación. Box-ball system we did with Leonardo Rolla, Nguyen, Chi Nguyen, and Min Wang. Okay, run. Well, you can think that this is just one line that follows. It's a one dimension, but so the line finishes there and then continues there. Okay, it's only one line. Baja un poquito.
Por alguna razón no funciona.
No, que hay que ponerle, hay que subir un poquito.
Sí, pero no funciona.
Ahí ponerle run simulation. Ahí está. Okay. So the box-ball system is something that is a carrier that transports balls. And then you can see that the big solid, so you can, these solidons that we identified here in this talk, you can identify at each time of the process. And here they are not even identified as solitons, but you can see them traveling. This is a simulation done by Leo Rolla and some students. You can find it in the Leo Rolla web page. Okay, we with Leo and Min and Chi, we are able to compute the speeds of the solid. All these speeds satisfy a system of linear equations that is related, that is universal behavior, Spon told us. So, okay, thank you very much.
Thank you, Pablo, for this pedagogical and very interesting talk. Are there any questions or comments? Yeah, Omar?
Can you apply this kind of pattern in iterative decomposition and work to Brownian motion?
Yes, we are working on that. Yes, you can do that. You will get the point process, the composition is a point process. But work in progress with Inés Armendariz and Pablo Blanc from Buenos Aires.
Okay. Other questions? Actually, I think it's related to Omar's question. So what is the scaling limit of these kind of things? Because this will be related to CRT and things like that, I
well,
guess.
The speeds, no, the speed is a lower class number, so you scale time and space in the same way.
Okay.
But if you want the Brownian motion, you have to rescale the initial configuration, the drift, because you need Brownian motion with drift. So you need a Brownian motion that is going down, so that you have discussion of this Brownian motion, and you have to rescale diffusively, but you have to rescale the parameter also. The lambda must rescale with the space and time to get the Brownian motion.
Well, let's thank again Pablo for this very nice talk. Thank you.